Welcome back to Orlando Math Learning Academy, and today I'm going to talk to you about chapter 3 of the college algebra textbook. And in this chapter we will be talking about the 6 basic function and its graph. So basic function and graph. Okay, so we already learned in chapter 1 and chapter 2 one of the basic function is the linear function. So basic function, and we also want to investigate the domain and the range of this basic function. Okay, so the first basic function, I just want to do a quick recall. The first one is a linear function. Okay, and the basic linear function is fx equal ax. Okay, a is a constant. Okay, and the graph of this function, of course, is a line, and this line goes through the origin of the coordinate system at 45 degrees. And as you know, that if a is positive, it will be increasing, or if a is negative, we have it decreasing. Okay, this is a is negative. So as you see, when I write fx equal to ax, I did not include the b, which is the y-intercept value. That's why the line must go through the origin. Okay, if I include the b, that it's gonna cut somewhere on the y-axis. Okay, and the domain for the linear function, it of course is from negative infinity to positive infinity. Okay, because every point on the x-axis, we can define a point on the line. Every point here define a point on the line. Okay, and so on for this too. And the range, of course, is also from negative infinity to positive infinity. Okay. The second function is quadratic function. And the quadratic function has general form fx squared, or sometimes we have ax squared plus bx plus c. Okay, I will tell you the difference between ax squared and ax squared plus bx plus c. So if the function is in the form of ax squared only, the graph will go through, it will touch the origin like this if a is positive, or like this if a is negative. Excuse me. And for the graph of full standard form of quadratic equation, it will cut somewhere. It could be it doesn't have to touch the origin. Okay, this could be something like this. It could be something like this, depending on the value of a, b, and c. Okay, however, no matter what, if it's in this form or this form, the domain of ax squared will be negative infinity to positive infinity. And however, the range will be different. The range for the ax squared will be from 0 included to positive infinity. For this, the domain is also from negative infinity to positive infinity, because every point on the line or every point on the curve I can define a value on the x-axis, or you can say every point on the x-axis I can define a point on the curve. Okay, have the same meaning. However, the range will be different. The range will be whatever from the bottom up. Okay, so it will be whatever the point here. So I just call upon whatever the value here will be. For example, value over here is negative d, for example. Then will be whatever from negative d to positive infinity. Or it could be upside down, and whatever the maximum point to negative infinity. We will explore the meaning of maximum and minimum later in this lecture, on the second part or this third part of this lecture. Okay, and the third function I want to introduce is the cubic function. And the cubic function has the form y equal x to the third power. This is a very basic form of the cubic function. Of course, they have the full standard form of cubic function, but I don't want to mention that at this moment yet. Okay, so right now you just learn y equal to x to the third power, ax to the third power, I'm sorry. And if a is positive, if a is positive, the cubic function look like this. And if a is negative, the cubic function look like this. And domain and range will be from negative infinity to positive infinity. Okay. Next. Next we have radical function. Fx equals square root of x. Okay, and if we graph it by using the table, I will obtain the graph like this. Okay, and the domain of radical function is from positive 0. From 0, I'm sorry, from 0 to positive infinity, including 0, and the range is also from 0 to positive infinity. Okay, because we include this one. The reason that we still can take square root of 0, because when you take square root of 0, give you 0, so it's still defined. Okay, so you see every point on the curve we can define a value on the x. Every point on the curve we can define a value on the x. Okay, number 5. Cube root function. I just want the graph of the cube root function can be obtained by the table, and it look like this. Okay, so the domain is from negative infinity to positive infinity, and the range is negative infinity to positive infinity. And cube root function look like this. Okay, you can plug in a point in order to graph the cube root function. Okay, number 6. Absolute function. You already learned the concept of absolute value. When you take the absolute value of any number, it always gives you positive number. That's why the graph of absolute function is always positive. It means it's always above the x-axis. Okay, above, at least on the x-axis, or above the x-axis. Okay. And the graph of absolute function fx equal to absolute of x look like the following. Okay, and this angle here is 45 degrees. Okay, so this is a very basic form of absolute function, and the domain of this, of course, with negative infinity to positive infinity, the range is 0 to positive infinity. I want to add a little bit more information. I want to introduce a full vertex form of absolute function. I don't know if I should do that, because it probably later on you will learn it in this book. But I think I just go ahead and introduce that standard form, a vertex form of absolute function. So any absolute function has the form ax minus h plus k, with the vertex has coordinates h and k. Okay, and the a is called the slope. Okay, it's called the slope. So by looking at this form and this form, we can see that the basic absolute function fx equal x absolute of x is the baby version, the baby version of this version, with a value equal 1. You see right here, and the h and k is 0 and 0. That's why the vertex is at the origin. Okay, when you graph this full vertex form of absolute function, the vertex is not at 0 and 0 anymore. However, the domain, you will have the same domain, will be infinity to positive infinity, and the range is different. The range will start from whatever the vertex you have. Okay, if the vertex is over here, the y coordinate of the vertex is k, so the domain will start from k to either positive or negative. Okay, either way, positive. If it open up, then we start from k to positive infinity. If it open down, then we start from k to negative infinity. Okay, number 7. Rational function. X equal 1 over x. Okay, so again, this is also a very basic rational function. We will investigate more and look into rational very deeply in the next few chapter, but right at this moment we just need to investigate the very basic one. Okay, and the graph of rational function look like this. Okay, we have two curves. Okay, and the x-axis and the y-axis becomes the horizontal asymptote and vertical asymptote of rational function. Okay, and the domain is from negative infinity to 0, because you see there, it never cut here. It never cut the y-axis, so this stop at 0, not included, unit with 0 to positive infinity, and the range is also from negative infinity to 0, union with 0, positive infinity. Okay, and the axis and y-axis are asymptote of the basic rational function. I want to add and introduce another function. I know that this function is not in the textbook, but I think this is very important basic function you need to know. It's also a rational function, but it's kind of another version of rational function. Okay, and this function has the form fx equal 1 over x squared. Okay, and this function has the form that has the function has the graph that look like this. Okay, so the domain is from negative infinity to 0, union with 0 infinity, and the range is from 0, not including 0, to positive infinity only. Okay. The reason I want to introduce this function to you because you will see this function a lot lately. I think so. Even you don't see that in algebra, in college algebra, but you will see it in calculus or pre-calculus. Okay. So I want all of you to memorize all of this function and their domain and their range, as well as their graph, and this is very necessary and it's very helpful to learn the other concept. Okay. So on the second part of the lecture today, I'm going to talk about another concept of function, and this concept is called it even or odd concept, even function and odd function concept. How do we know that a function is even and how do we know a function is odd? Okay, by observation, you see that all the function we have worked through so far is either sometimes it's symmetric about the y-axis, sometimes it's symmetric about the 0 at the origin. For example, this one is just like sometimes it's neither symmetric about the 0 or being symmetric about the origin. For example, in this case. But most of the time we have the basic function that is symmetric about the origin or symmetric about the y-axis. For example, this one is symmetric about the y-axis. I mean, when I say symmetric about the y-axis, it means that every point on the left branch, on the right branch of the function, and we mirror that about the y-axis, we have another point here. Okay, that's what it mean by symmetry. Okay, so by being symmetric about the origin or symmetric about the y-axis, we have the concept called even and odd function concept. Okay, number 2, even and odd function. So how we know the function is even and how we know the function is odd? We need to go through this definition. Even function. Okay. Definition. A function is called even function. Okay. what case? How we don't know that? Okay. Yeah, let me see. A function is even function. A function f(x) is an even function if f of x equal f of negative x. I'm sorry, f of negative x equal to fx. Okay. Okay. Example. F of negative equal to fx. Okay. Example. Okay. I have a function like this, and I want to see if this function is even. Okay, what I'm doing is that I will replace the x with negative x, and I want to see if it turned out to be equal to itself or not. Okay, so negative x squared is equal x squared plus 2. So x squared plus 2 basically equal to fx, right? So that's why it turned to become itself. Okay, after we replace the x with negative x, f of negative x become fx. So we can conclude that fx is even function. Okay. Okay. And all the even function property. The property of even function, all the even function is symmetric. Even function is symmetric about what? Is symmetric about what? About the y-axis. Okay. So we have absolute function is even function. We have quadratic function is the basic quadratic function is even function. Okay. Second, odd function. Definition. A function is an odd function if f of negative x equal negative fx. Example. I want to check fx equal to x cubed minus x. Again, I need to replace the x with negative x. Okay, and I want to see if it turned out to be negative fx or not. If it turned out to be negative fx, I can conclude as its odd function. Oh, and it is. So right here, x cubed minus x is fx, right? And we have a negative here, so it equal negative fx. So we can conclude that fx is odd function. Okay. Sometimes the function is neither odd nor even. So in that case, when we calculate f of negative x, it turned out to be either negative fx nor fx. Okay. Then and the graph of the function that neither odd or even is neither symmetric about the y-axis nor being about the origin. Okay. It is also about the graph of the function. In this part of the lecture, I want to talk about the highest point of the graph and the lowest point of the graph, and when this is called relative maximum point, and when this is called absolute maximum point. Okay, so number 3, absolute and relative max mean of function. Okay, so we need to see the difference between the absolute max mean of the function and the relative max mean of the function. When you hear the word absolute, of course you feel that is the highest point, right? Absolute max is the highest point of the function, and the absolute mean is the lowest point of the function. Sometimes we have another name called a global absolute. The relative maximum has another name called global global minimum or global maximum. Okay. But first, let's go to the definition of the absolute maximum of the function. Absolute max point is the highest point. Is the highest point of the function on the entire domain. Okay. So the absolute max, of course, the highest point, the highest point. Okay, and absolute mean point is the lowest point of a function on the entire domain. Okay, so if a point on the graph, any point on the graph that make the function, or we can say a location where the function changed the behavior from increasing to decreasing, or from decreasing to increasing, and then we call that relative maximum and minimum. Okay, relative max point is where the function change behavior from increasing to decreasing. Okay, and relative minimum point, relative minimum is where the function change behavior from decreasing to increasing. Or we can say that for the relative maximum, any point in the open interval, okay, of the maximum point, such that f of x is less than equal to f of that maximum. Okay, so what I mean is that, okay, for example, if a function has the relative maximum at point A, okay, then you take a small open interval, or an open interval containing A, then f of x always less than or equal to f of A, okay, for all x value. Okay, let me draw the graph of it. I think it's help you to understand the concept. So this is a graph that contain the contain the minimum, a relative maximum. Okay, right here. So this graph here has a relative maximum at the point I call the point A. Okay, because you see that the graph changes behavior from increasing to decreasing. Okay, actually they have two relative maximum, okay, and one relative minimum. So this is relative. Let me plug in the power. This is also relative max, and this is relative mean, because at this point it changed the behavior from decreasing to increasing. You see that? Okay. Now we want to take a small interval, an open interval. Let me zoom in the point A over here. Let me zoom them in. Okay, and I want to take an interval, an open interval around A. Okay, let me take this interval only. Okay, and you will see that f of any point here around f of any value around the point A, the point that contain, for example, the point A over here has the coordinate is x, okay, and it's y, okay. For any value about any value around the x component of the point A, okay, then f of those value always less than f of A. That's what I mean. Okay, so we can say that f of x is always less than equal to f of let me see, f of x1, okay, always less than equal to f of x. Okay, with x1 is x component that is inside the open interval around x. Okay. So this is x over here, so x1 over here. Okay, that's what I mean. So this is a pretty theoretical here, but I want you to understand that, because maybe later I think this is very useful also. So if you okay, in general, this is what I mean. For any, if you take any value, any x value about x in the open interval of x, then f of those value is always less than equal to f of x. Okay, because f of x is the highest point. Okay, it's the relative max. Okay. Okay, but and for the relative mean, okay, we can explain it in the same method. So this is x here. Okay, and this is I can take the open interval around x. Okay, let me zoom it up, zoom it in. So this is the point here, and point C here. Okay, and the interval, and this is point C here, has a coordinate is x. Okay, so there's the open interval over here. For example, I want to pick a point here. It's called x2. So we know that fx always less equal to f of x2. Okay, and x2 is the x value that is inside the open interval around x. Okay, so I think I'm going to use the word value is better than x component, because I feel x component is like a point. Okay, x value is better. Or you can think this way: any point here, any point around the point C here. Okay, for example, I name it C1 here. So any point C1, C2, C3 around the point C is always above point C. Okay, and for the relative max of any point around the point A, for example, point A1, A2, A3 is always below the point A. Okay. Okay. So that is a theoretical definition of the maximum, relative maximum and relative minimum. Okay. For the absolute maximum and absolute minimum is easy, because it's just the highest point and the lowest point. Okay, but in this case, for this example, for the graph I have it here, the point A is also the relative maximum and absolute maximum at the same time. Okay, however, for the absolute, we don't have the absolute minimum because the function is keep going down. Okay, so in general, that if you look at, if you investigate the graph and you want to see the function has the maximum or minimum point, it could be a point, it could be a maximum, the relative max and the absolute max at the same time. Okay. Okay. All right. Let me see. Let's do the example. Okay, let's do the example number 6 on page 219 over here. Okay, let me give. Okay, so they give you this function with the graph, and they want you to find the domain and range of the function. So for the domain, Okay, we want to check all the value that make the function define, or all the x value that you can draw a vertical line from that value to the line, to the curve. So you see any point on the x-axis we can draw the curve, we can draw a line. Any point on the x-axis we can draw a line here. So any point on the x-axis is corresponding to a point on the curve. So it means the domain will be from negative infinity to positive infinity. However, the range is different, because the range, we have the highest maximum point here, or the absolute maximum point here at point 4, and we don't have a lowest minimum point. So the range goes from negative infinity to 4, and we have to include 4. Okay, and I want to ask you what value of x is a relative minimum occurring. So relative minimum, so this is a relative minimum, because this is where the function change the behavior from decreasing to increasing. So the relative minimum is negative 3 to is negative 3 and negative 5. Okay, and it occur at x equal to negative 3. And what is the relative minimum? Oh, well, I already give you the coordinate. Okay, and what x value does the function has is a relative maximum. So the function has relative maximum at x equals 0. Okay, and as I already told you, this is also the absolute maximum. Okay, set any absolute maximum or minimum of this graph. So this graph has only one absolute maximum. However, we have two relative maximum. Okay, and one relative minimum. Okay, and we don't have absolute minimum, because this function is keep going down. So we have only one absolute maximum here. Okay. Okay, so this seems to be very easy. By just look at a graph, we can tell whether the function is increasing, or function has a maximum or absolute maximum, and so on. We can also find the relative maximum and minimum point on the graph using the graphing calculator. So if you hit, if you go to I don't have battery anymore. So but it's around here. If you hit the second trace, and it gives you a window that tell you the maximum and minimum, then you just hit that, and then it gives you the answer. Okay. Okay. For the practice part, so number 4, practicing. Okay. I want to pick one of the problem on page 227. Okay, I think I will be doing number 22, I think. Okay, number 22, and I want to check the function fx equal to x to the 4, 2x to the 4 plus 3x squared is even or odd. Okay, so again, according to the concept, I replace the x with negative x. and I can see that it turned out to be the same, right? Because when you take negative and you square it, it gives you positive. So this is the fx equal to f of negative equal to fx, so this is even function. Okay. And I want to do the 18 now, so I want to find the domain and range of the function fx equal to square root of x plus 3. As we already learned that we cannot take square root of a number that is negative, so everything inside the radical, we call it the radicand, must be greater than or equal to 0. So x plus 3 must be greater than or equal to 0, and we solve it this inequality. Okay, and we want to express the algebraic expression here, algebraic inequality expression into the interval notation. So it will be from -3 to positive infinity. So that will be the domain. Okay, and let me see. So number 28 is look like one of the example we already learned during the lecture. On page 228, I want you to state the domain and range of function and find relative max and relative mean. Okay, so that seems to be very easy also. I think that, yeah, so yeah, so most of the question is seem to be very easy. If you have any question, you just let me know, and if you have any concern or part you don't understand, just put your comment under the YouTube video, and I will go through that with you. Okay, so basically we finished the first section of chapter 3, 3.1. so in the next video I'm going to talk about section 3.2, and if I have time I might jump to section 3.3 also. So that's all for the lecture today. If you like the video, please go ahead, subscribe to have more video lecture video in the future. Okay, and I'll see you next time. Thank you. Bye bye.